Okay, we're starting. We're going to talk about maximums and minimums today. Point two.
Like the one I was like, was like this.
Let's see.
With the shift
Yeah, the shift was
I
like
have absolutely no idea.
There are two kinds that we're going to care about, so-called absolute maximums and minimums and so-called local maximums and minimums. So let me tell you what those guys are. Probably illustrate them with pictures. So there's a function and I give you an interval, some closed interval. And we can say it has an absolute maximum. Another word for that, I'll usually use the word absolute, but there's another word. It can also be called global maximum. At x naught, if the y value at x naught is the largest y value on the interval. Right, so the biggest y value that you attain, that the function attains, is called the absolute maximum. Right? Absolute or global minimum is final similar. So that's basically it. The absolute max is the largest y value your function will attain. The absolute min is the smallest value your function will attain on the entire interval, right? So there's always some interval that you're considering. Okay? By contrast, we have something that's called local maximums and minimums. And that's more like when you're zooming in. It's the maximum in its region. So again, f of x is defined on AB. And of course your x naught here is in the interval. Just that should be clear. If it's defined on AB, we say f of x has a local maximum. Another word for that is relative. At x naught in AB. If f of x naught is the largest y value in some small region or interval contains local or relative min is defined similar. So we just define both absolute maximums and minimums and relative maximums and minimums. And absolute is in a global sense. If you take a look at the big picture and look overall, who's the highest y value, who's the lowest y value, you're finding the absolute maximums and minimums. But if you're looking at locally, for little hills and valleys here and there, then you're trying to locate local maximums and minimums. And both have their place and their uses. But that's basically it. So the idea is, let's do some illustrations here. Function, here's A. And I can say my functions here is this. Say that's how my functions look versus these are just a few figures for you to kind of see the idea here. So if you're looking at this graph, let's look at the first one. So if you were to describe the points on this one, for example, that is an absolute maximum. You identify an absolute maximum point, what do you say? Yeah? Right, it's at A, right? This here is the highest y value. This here would be your absolute max. Right? Notice that when you're looking in the big picture sense, this is the highest y value that your graph attains. Is there an absolute min? Yeah?
The point just below B on the x-axis.
Right here, the guy that's kind of touching the x-axis here, this is the absolute min, right? He's the smallest y value in the global sense, right? Now let's talk about locally. What do you see locally? Any local maximums and minimums? Yeah?
There's local minimums, the absolute minimums, one local minimum, and the other local minimums, closer towards the end.
Right, that hump right here,
Yeah.
right? So notice that this is a local minimum, right? So it's not the smallest guy overall, but if you kind of zoom in and just look in a small region surrounding that point, the depth of that valley is going to be the smallest guy in that region, right? You'll notice that here, if you zoom in, the top of this curve here will be a local maximum. Notice that if you zoom in here, you'll also have a local minimum, so this point is both an absolute minimum and a local minimum. He's both the smallest guy overall, but he's also the smallest guy when you zoom in. And that's pretty much always going to be true for the absolutes. You can also think of them as a local. Right? And this guy is not really anything. He's neither the biggest guy or the smallest guy. I mean, if you allow to go a little bit outside of your interval and look in that region, then that guy would be a local max. Right? But that's the difference. There's a global sense when you're looking at the entire picture overall, and then there's a local sense where you're just looking in very small regions surrounding points. And both of these have significance. What about this guy? Any absolute maxes? Yeah?
Just the
Right.
the
The apex here, the vertex or whatever. Right, this here is an absolute max. It's also a local max. Any absolute mins, local mins? Notice here there are no minimums. Neither absolute nor local, right? There's no point on this graph that in any small region or overall, it's the smallest guy ever, right? Notice that this guy will just keep going down. So no matter what y value you pick, there will be a y value that's smaller than that. Okay. This guy? Absolute max. Yeah. That's your absolute max. Absolute min. At B. Any local minimums? A y value that's the smallest in its region. Yep. At A. That's it. What if I tweak this slightly? And instead, I didn't fill in any of these points. Would that change your answers? Yeah? What would your answer be now? Who's the absolute local minimum?
It would be, the absolute maximum of the value as x approaches whatever point like between A and B is like the point that's not filled in.
No point is filled in. Right,
Yeah.
meaning this
So
is
it's
not
a-
a part of the function.
Yeah, so it would be as x approaches that whatever value, like there's no value marked for the absolute.
Okay, so there's no value on the graph. Like, the definition doesn't involve limits, so it's not an approaching kind of thing. This one actually has no maxes or mins. Right? You're approaching a point, but if you ever pick a point on the graph, there will be a higher point on the graph, right? You're approaching this point, but you'll never get to it, right? So it's like, if you pick a point that's on the function, there's a point that's closer that's on the function. And if you pick that, there's a point that's closer that's on the function. There's a point that's closer. You're always getting closer to this point. You're never really getting it. You'll never actually attain, okay, this y value is the largest y value. The y values are always getting larger, right? But they have a limit. But the limit is not a part of the function, so we can't say it's a maximum of the function. It's not on the function. So it has to be a point on the function. It is a y value in the function, right? So this, while this would seem like the peak that the function will attain, it's not a y value on the function. There's a gap there. So we can never actually attain that value. So that's sort of the idea. But globally, the biggest and smallest guys that are on the function, they're defined in the function. That's your absolute max or min. And if you kind of zoom in locally and look piece by piece, and you're noticing bigger and smaller guys in some region, those are the local maximums and minimums. Yeah.
Depending on where you define your small region containing a time to be, couldn't you make any point a local max or min?
No. I mean, like if I pick this point over here, that will never be a local max or min, right? If I zoom in here, is this point the biggest point? No, because that point is higher. Is it the lowest point? No, because this point is lower, right? Let's say if I open up some small interval containing that point, if I set that to my x naught, this point is smaller than that, so it's not, that can't be a minimum, while this point is larger than that, so it can't be a maximum, so it's neither. Right? So it's not a thing that any point, you can kind of finagle things to make any point attain this property. It's just not true that any point will attain. Yeah.
Except if you set the intervals, right? Just like if it were like the maximum from 1 to 4, and that point's at 4, or at 1, that's the max there.
Sure, but in general, we won't assume that we know what's happening outside the interval. It's possible that this function does something over here, where if we shift the interval, we get a different maximum, but outside of here's dark zone, we really don't know what's going on, right? So we're really only describing a part of the universe that, okay, this is what we know. Outside of this, we don't really know. And it's not correct to assume that, oh, if we were to continue, we'd go up. You don't know if you'd go up. You could make a sharp turn and go down. You can't assume outside the interval. So it's really something where we're on an interval that we kind of know what's happening, and I just want to locate maximums and minimums on that interval. Right? Outside the interval, I don't know what's going on. So that's just an illustration of what these are. Locating things like this, absolute maximums and minimums are important, and we'll look at some. Well, we've already seen some application of that, right? When we're doing things and we want to find what's the maximum profit, right? It's really finding the maximum of some function. Or where can we have the minimum cost? It's finding the minimum of some function. So finding maximums and minimums are important. You need to know how to identify them on the graph, but more importantly, you need to know how to find them on a graph, probably without even drawing the graph itself. And to that end, we have some theorems that can help us out, as well as calculus. So there are many important theorems in calculus, but we're not even going to cover a lot of them. I'm going to talk about two of them without proof. There is the extreme value theorem. And this one says if f of x is continuous on AB, then f is So there's a theorem that tells us that in certain situations we're guaranteed to be able to locate these guys. We're guaranteed that they exist. It's not always exist. Remember there was a question down here where I told you there was no max or min, there was no absolute max or min. And the reason is because it failed on this condition. It wasn't continuous on the entire integral. Right? But it turns out that if your function is continuous, you're guaranteed to have these guys exist. Right? It's impossible for it not to happen. So that's called the extreme value theorem. So that kind of tells you when you know that searching for an absolute max or min is not a waste of time. Okay. And this is a while ago, but does everyone remember what it means to be continuous? Like in the mathematical sense? Yeah.
You can draw without thinking about it.
The mathematical definition. Yeah?
There are no holes.
Yeah, but the math definition. Like how we can describe it in terms of an equation that you can check. Yeah?
It's defined everywhere. Like x is defined everywhere all at x.
Yeah, but how would I check? Yeah?
Isn't it f of x equals negative x or something?
No. When that's true, that's called an odd function, not a continuous function. It has to do with limits. This means that the limit as x approaches a of f of x is equal to f of a. Meaning the limit as you approach the point is equal to the filled-in value of the point. And that means you can always draw it without the multiplication. And this happens for all points in AB. So to say something is continuous on AB means that this condition is fulfilled for every point on the interval.
What if your line is just flat? Then is there an absolute maximum?
Yeah, if you're horizontal, it's a kind of a technicality, but literally every point is going to be your absolute max. Every point is as big as every other point, and every point is as small as your other point. So technically speaking, everyone is as big as it can get or as small as it can get, and you can choose any point to be an absolute maximum. But that's just a technicality.
Okay, it seems like a cop-out.
It is a cop-out, and it's usually not an interesting case. It's not usually something that someone would ask. If they know it's a constant function, no one would ask, so what's the maximum we can get? Like it's always 5. I don't know why would you ask that question? Yeah. So mathematically, it's kind of like anyone can work, but in practice, no one would even ask the question in the first place.
Can you put that on the test as like an extra credit question?
We'll see. Yeah, that would be funny if someone says, you know what, it's at x equals 5. Yeah, then to be wrong, you'd literally have to pick a number outside the interval. I don't know if anyone would do that. There's another important theorem. There's also Fermat's theorem. Not Fermat's last theorem. I don't know if any of you are familiar with Fermat's. Does anyone know about Fermat's last theorem?
I've heard of it. I don't know what it is, but
Wait, is that the guy that like
died before he could prove it. Is that one?
Isn't it like
He's the guy who claimed he proved it, but
Yeah.
no one found the proof.
Did he
And
claim he
then
proved it like the
eventually-
margins of
So
the
that he wrote it in like the margin of this book. Hey, I found this amazing mathematical
Didn't-
fact.
didn't somebody-
This is the fact,
Didn't-
but I'm not gonna prove it. And he just wrote that in the margins, and then like it
Didn't-
drove mathematicians crazy for like 300 years. People were trying to prove this thing.
Proved it, right?
Someone did prove it
British
eventually.
guy.
That's Andrew Wiles. I think he's a mathematician at Cambridge, but it was like 300 years later. Like no one ever. It seemed to be true, but no one could prove it, and this guy just sent everyone on it. Yeah, that's the same guy, but this is not the theorem that he's famous for. So,
There you go.
and that was called Fermat's last theorem because it's the last theorem that no one could prove that this guy mentioned. It was like an amateur mathematician. He wasn't even like an actual. He just did it for fun. But anyway, he came with another theorem that says the following: if f of x has a local max or min at x naught, then it turns out that f prime, the derivative evaluated at that point, will be what? Does anyone know? It will be 0. Right, as long as the derivative is defined, and you know you have a local max or min somewhere, it turns out the derivative will be 0. And this can kind of make sense. If you look at a picture, right, and you pick that highest point, and draw a tangent line, it's going to be a horizontal tangent line. The slope of that line will be 0. There's a warning though. The converse is not true. i.e., if we know f prime of x naught is equal to 0, it does not mean that it's a max or a min. I can give you a very simple example for that case. Look at y equals x cubed. Right? That graph looks like this. So if I find f prime here, that's 3x squared. And if I set f prime equal to 0, I get 3x squared equals 0, which means that x equals 0. But notice here that at x equals 0, that's neither a maximum or a minimum. Okay? So just because your derivative is 0 does not mean you have a maximum or a minimum. Okay? But it goes the other way. Like if you know there's a maximum or minimum, it turns out your derivative will have to be 0 as long as it's defined. It's also possible for the derivative not to be defined, and you can have a max or a min. An example of that we saw earlier as well. If you look at y equals absolute value of x. We've already proven that at this point there is no derivative. The derivative is not defined at that point, but that's clearly a minimum. It's a minimum, but f prime does not exist. So there's this wonderful theorem, but it seems almost useless as stated, because there are cases where the thing that we can easily check doesn't work out, and there are cases where we can't check it because the derivative doesn't even exist, but there are maximums and minimums. But it's still important with the aid of two things. So you have to be careful how you're applying Fermat's last theorem, but this means In general, what we want to do is we want to find where the maximums and minimums are, so we won't know where they are in the first place, and so the theorem seems useless. But we can apply Fermat's theorem directly. Enter. There are two main tests that helps us do this. There is the first derivative test. There's the second derivative test. Now let me state those tests for you. And well, before that, I need to talk about the definition, and then I can state the test. So obviously, there are 2 points that are important to us. Fermat's theorem tells us that where the derivative is 0 is an important point to look at because there might be a max or a min there. But also when the derivative is undefined, there might be a max or a min there, but we have to somehow check. So it turns out that these 2 kinds of points, we're going to give them a special name. Does no one know what they're called? Called a critical number. If one of these 2 things happen. If our derivative is 0 or our derivative is undefined. If you look at the point, the coordinate that you care about, it's called a critical point. Now I can say the first derivative test, the second derivative test, and we're also going to do the closed interval method. Now I'm going to state the test for you and then we're going to use it. I don't know how many examples we'll get through. So these 2 tests, you're using them to find local maximums or minimums. You can use either or. You don't have to use both. But I'll describe each of them to you. In practice, I think it's generally better to use the first derivative test because you already have this before you have the second derivative anyway. But you can use either one. And there's a third method for finding absolute maximums and minimums. So let's talk about to find absolute maximums and minimums. There's what's called the closed interval method. So if f of x is continuous on B, which remember it guarantees that we have an absolute maximum, then you can locate where the absolute maximums and mins are by the following. 1. Find the critical points in AB. And Evaluate. Right? Evaluate, that means find the y value. Plug them into the function and find their values. 2. Find f of a and f of b. Right? Evaluate the function at the endpoints. 3. Compare. And so in that case, the largest y value is equal to your absolute max. Right? So you'll have two sets of y values to compare, and the smallest y value is your absolute min. That's called the closed interval method. I'll do some examples after we state all the methods. So this is the method for finding absolute maximums and minimums. It works when your function is continuous on the closed interval, because that's when you're guaranteed to be able to find it. To find local maximums and minimums. And you can refer to that long ago when I gave you that table of all the derivatives. Here's what f does, here's what f prime does, here's what f double prime does, and all the things they can tell us and how you can find them. We're going to put all that knowledge now into these theorems. There's method 1, first derivative test. That one says the following. So you're going to find the critical points. Find all the points where the derivative is 0 or undefined. You're going to test these points. Now I like testing them on an interval because it gives a nice pictorial picture. Test these points on an interval. Conclude based on the following. So again, let's say you find a point. That's x naught, that is your critical point. Right? So this is a point where the derivative is 0 undefined. What you're going to do is you're going to test it on an interval in the first derivative. So you're going to pick a point slightly to the left and slightly to the right. Right? So you're going to try x1. You find the derivative of x1. And you pick a point to the right, x2. Find the derivative of x2. Right? So you're going to find the critical point is here. That's where your derivative is 0 or undefined. Find 2 points to the immediate left and right of that. Any point will work usually, once it doesn't go into another interval that you don't want to do. Find the derivative there, and based on the signs, you can talk about what's happening. So for example, if this is positive here and negative there, that means your function is increasing, right? Because positive derivative means increasing. Negative means decreasing. So this guy will give you a maximum. Right? A maximum will behave like this. Conversely, if this is your critical point, and you can pick a point to the right, to the left and the right of it, and you can find the derivative. If it's negative here, but positive there, it means here it's decreasing because the derivative is negative. Over there it's increasing. And you would plug it, make sure you're testing it not into the original function, to the derivative of the function. And this is what a minimum would look like. In fact, it's local, of course. So that's using the first derivative to identify local maximums or local minimums. You can actually use the derivative to do it. And this is how you do it using what we call the first derivative test, because you're testing everything in the first derivative. So you find all the critical points, you do that by using the first derivative, plot it on a number line, and plug in points to the left and right of it into the first derivative. The signs will tell you where things are increasing or decreasing. If you're increasing then decreasing, you had to hit a maximum here. And if you're decreasing then increasing, you have to have been a minimum. Provided your function is continuous, of course. I don't know if I said that. Because if there's a gap or a hole, I mean, it's not going to matter. There's another method. The second derivative test. As the name suggests, in this test you're going to use the second derivative. Personally, I pretty much never use this, but some people like using it, so I'm going to tell you about it anyway. Suppose f is continuous. Secondly, f prime at x naught is defined and it's actually equal to 0. And f double prime is continuous. Around x naught. Then the following features will happen. If your second derivative evaluated at the point is positive, anyone remembers what that means when the second derivative is positive? Yeah.
So the trend is upward, moving
Right.
upward.
Concave up like a cup, you shape like a smiley face, right? So that would kind of tell you what is the kind of point you're looking at, a minimum. You have a local minimum. Turns out if you evaluate the second derivative at the point and it's negative, negative means down, you're concave down, you're negative side, your frowny face means you shape like this, which means you'd have a local maximum. F double prime at the point equals 0. You can really get no info from this test. You have to try something else. So the thing is with this, you'd have to have passed through the first derivative to get to this anyway. So I usually, because I'm doing the first derivative anyway, I usually just use the first derivative. I never get to use the second anyway. But some people like doing it. You can just plug a number into your second derivative. If you know it's a critical point, then if the second derivative is positive, it's a minimum, a local minimum. If the second derivative is negative, it's a local maximum. We have only time for one example. So a problem like this will be on the next test. It's not a complicated kind of problem, but it's a very standard problem to ask. I'm going to give you with a very easy function, but the principle is the same no matter what. Just look at the quadratic. And I'll give you an interval. Find the absolute maximum and minimum of f. So it asks about absolute. So that just means I'm going to use the closed interval method. So 1, I'm going to find the critical points and test them. So I find f prime, that's equal to 2x. If I set f prime equal to 0, I get x equals 0. Set f prime undefined, no solution, right? Because it's a polynomial, it's always defined. So 0 is my only critical point. So then this would mean I would find f of 0, which I know is 0 squared, which is 0. 2, test the endpoints. So I'm going to find f of minus 1, and I'm going to find f of 2. This is minus 1 squared. This is 2 squared. 3, compare. Who's the biggest and who's the smallest y value? Right? These are my 3 y values of consideration. The smallest one is what?
0.
0 is the smallest one, so you literally write that down. F of 0 equals 0 is the absolute minimum. The largest is 4. So you would write f of 2 equals 4. Usually express the entire thing like this. F of the x value equals this y value is what? And that would be your answer. So there will be a problem like this that it's always solved this way. It's not going to be anything complicated. At this point, finding a derivative shouldn't be any problem. Solving the equation with it equal to 0, I don't assume should be any problem. And then you're just plugging in numbers. The smallest one is your absolute min, the largest one is your absolute max, and that's it. And we'll stop there. Actually, I'll give you some handouts that you can read through and maybe try a few problems and bring next week. I don't want to have to bring them again. So this is the outline for what we're going to be doing. We're going to be using a lot of this stuff. So I'll do some examples on local maximums and minimums, and then we'll do curve sketching.
Like what I found with
So bring these back on the sheet of 12.
This will be my own assignment. If you okay, good luck.
Okay, so we're done.
Cancel that pressure.